Welcome back to the deep dive. Today, we're kicking off something really important in our CSWIP 3.1 exam prep series. Our goal isn't just, going over answers. It's about equipping you with that core welding knowledge that really sinks in, the why behind the what, giving you a proper edge for your welding inspector exam. We've got a few common multi-choice questions lined up that really test if you understand the basics, not just if you've memorized facts.
Exactly. And think of this as a practical guide. We're going to peel back the layers on these questions, not just tell you the right answer, but give you the context, the insights, make it genuinely useful on the job. Because passing the exam, that's one thing. But being an effective inspector out there, someone who can really problem solve, that's what counts.
Absolutely. Getting past just remembering stuff to really getting it. All right, let's jump in. First challenge is about gas metal arc welding. Question 1. The spray transfer mode of GMAW is characterized by John of Height. And your options are A, giving deep penetration, B, being suitable for positional welding, C, giving excessive spatter, or D, all of the above.
Okay. For any inspector, really understanding these different modes is, it's fundamental for checking quality and making sure the right process is being used. Here, the key feature, the defining one, is A, giving deep penetration.
Deep penetration. Okay. Welders like that, I know, but for an inspector, what does that really mean, that deep penetration? And how does spray transfer actually achieve it? It feels like it's more than just turning up the heat, right?
Oh, absolutely. For an inspector, deep penetration isn't just jargon. It means you're getting excellent fusion right through the joint, which is great, especially for thicker stuff where you need strong, full-strength welds. The way it works is pretty neat, actually. Spray transfer uses high current and voltage settings. This creates this really hot focus arc, and it propels a constant stream of tiny molten metal droplets straight from the wire into the weld pool. Think of it like a focus spray of molten metal. That force plus the intense heat drives it deep into the base material. So when you're inspecting, you're looking for that consistent deep fusion. That tells you about the structural integrity. If you see anything that looks like lack of penetration on a weld that should be spray transfer, that's a big red flag. It means something's off with the parameters or technique.
That makes perfect sense. So an inspector seeing shallow penetration where spray transfer is specified might think, okay, maybe the setup's wrong. Maybe they deviated from the procedure.
Exactly.
What about those other options then? I've heard people sometimes mix up spray transfer with high spatter.
Yeah, that's a really common mistake, actually. And it's good for inspectors to be clear on. Option C, excessive spatter. Definitely not spray transfer. In fact, it's known for being very clean, very low spatter because the metal transfer is so smooth. If you do see lots of spatter on what's supposed to be spray transfer, that's another clue for you, the inspector. Maybe the shielding gas isn't right, or the voltage is off, or the wire feed speed doesn't match. It's valued for being efficient and clean. And option B, being good for positional welding. Generally, no. Some pulse versions can handle positions better, sure, but standard spray transfer. It creates a pretty big fluid weld pool because of all that heat. Imagine trying to keep a runny puddle of metal stuck overhead against gravity. It's tough. The metal wants to sag or drip, making it super hard to control the bead. So mostly, spray transfer is for flat and horizontal welding, where gravity helps you out. Knowing that helps you check if the right process is used for the job's position.
Right. That fluid weld pool explanation really clicks. It's basic physics, isn't it? Okay, sticking with positional challenges. Let's look at a pipework scenario. Question 2. In positional MMA welding on pipework, welders are having difficulty in obtaining good capping profiles when welding in the overhead position. You would. Options. Advise them to increase the current. B, advise them to increase the voltage. C, ask for a new welding team. D, suggest the use of a smaller diameter electrode.
Ah, yes. A classic problem you might encounter right there on site. This really highlights the kind of practical decision-making an inspector needs. The best advice here is D. Suggest the use of a smaller diameter electrode.
Okay, now for someone maybe newer to inspecting, that might seem a bit backwards. You're struggling, so maybe you think you need more power, a bigger electrode to fill it faster. Why is smaller the way to go for overhead caps?
It really boils down to control. And managing gravity, that's everything in overhead welding. When you're fighting gravity using MMA stick welding, every drop of molten metal just wants to fall down. A smaller diameter electrode naturally makes a smaller weld pool, and a smaller pool is just easier to manage. It cools and solidifies quicker, giving the welder much more control. They can place the metal precisely, build up that cap profile without it sagging all over the place. It's really about finesse, not just brute force, especially for that final cap. Now, if you suggested options A or B, increasing current or voltage, you just make the weld pool bigger, hotter, more fluid. That would make the problem way worse. But I'll guarantee a bad cap profile, maybe defects like too much convexity or undercut, things an inspector has to reject. And option C, asking for a new team. Well, maybe tempting if things get frustrating. But a good inspector tries to solve the problem, guide the team first. So yeah, understanding how electrode size affects the weld pool in tricky spots, that saves time and avoids rework.
Makes sense. It's about giving the welder the right conditions to succeed, making it easier to control. Great example of physics informing practice. Okay, from technique, let's talk about the tools themselves, the electrodes. Question 3. MMA electrode can be grouped into 3 main types. These are options: A, basic, cellulosic, and rutile; B, neutral, cellulosic, and rutile; C, basic, cellulosic, and neutral; or D, none of the above.
Right. This is really foundational stuff for anyone in welding, but especially inspectors checking material usage and potential quality issues. The correct grouping you need to know is a basic, cellulosic, and rutile.
Okay, basic, cellulosic, rutile, they're not just names, are they? They dictate how you weld. For everyone listening, what's maybe one key thing, or even a common pitfall, an inspector should really be aware of for each type?
Good question. Knowing the difference helps you understand why an electrode was chosen and what risks might come with it. Let's start with basic, often called low hydrogen electrodes, right? Their coatings produce weld metal with very little hydrogen. That's critical for stopping hydrogen cracking, especially in things like high-strength steels, pressure vessels, thick sections, really important stuff. What sometimes gets missed but is vital for an inspector is storage. They must be kept dry, usually in heated ovens. If you, as an inspector, see basic rods just lying around exposed to the air, that's a big potential quality problem. Moisture kills their low hydrogen benefit, introduces cracking risk. Then you've got cellulosic electrodes. People sometimes call these the digging rods. They give a really forceful, deep penetrating arc. Lots of smoke, a bit more spatter usually. Fantastic for getting deep fusion, so they're often used for root passes, especially in pipelines, and for welding downwards quickly. One advantage: they can sometimes handle joints that aren't perfectly clean or fitted up because that strong arc can kind of burn through stuff. An inspector on a pipeline job would expect to see cellulosic for those tough root passes. Speed and deep fusion are key there. And finally, rutile. These are generally seen as the easiest to use. Smooth arc, nice looking bead, slag comes off easily, great for general fabrication, maybe where appearance matters more, often liked by learners. They don't penetrate like cellulosic or have the low hydrogen of basic, but for ease of use and looks, they're good. An inspector might check these welds carefully for slag inclusions, though. If the slag isn't cleaned properly between passes, it gets trapped, and that's a defect. So yeah, each type has its place. Understanding that place helps you judge if the right consumable is being used and check for the relevant quality issues.
That's a really clear breakdown. It's not just what they are, but what an inspector needs to actively look for when they see them used. Okay, shifting gears now to something absolutely vital: safety. Question 4. What are the most common welding hazards? Options: A, fumes, burns, electric shock; B, only fumes; C, only burns; D, only electric shock.
Yeah, for an inspector, safety isn't just ticking boxes. It's about protecting people. Simple as that. The correct answer absolutely is A. Fumes, burns, electric shock. It covers the big 3.
Right. It seems obvious, but maybe it's easy to focus on just the bright arc. As an inspector, what are some of the maybe less obvious signs you'd look for? How do you spot inadequate protection against these 3 hazards on a site?
That's where the inspector's detailed observation comes in. For fumes, sure, you see the smoke plume, but you look deeper. What's the overall ventilation like? Is someone welding in a tight space without proper air supply? Is the fume extractor actually positioned correctly, close enough to work? Or maybe it's just not powerful enough for the material, like stainless or galvanized steel. Those fumes are particularly nasty with chromium, zinc, nickel. An inspector might not just look, but ask for air quality reports or check that the right PPE, like proper respirators, is being used and looked after. With burns, it's not just direct contact with the arc or hot metal. Think about arc flash. Are the helmets properly rated, actually down when welding? Are screens up to protect others nearby from UV burns, that welder's sunburn? Are hot work permits done? Fire watch in place? Any hot parts lying around someone could touch by accident? Sometimes it's the scattered hot slag or just radiant heat causing burns. So good housekeeping, proper shielding screens are crucial. You check the area is clear of flammables too. And electric shock. Potentially fatal, right? Often down to equipment condition. An inspector has to look closely at cables, any fraying. Damaged insulation. Is the ground clamp good, making proper contact? Is the machine earthed correctly? Is the area wet? Are welders standing in water, wearing dry gloves? It's about finding any potential path for electricity. and making sure it's blocked. These are all areas where an inspector being vigilant can literally save a life.
It really underscores that need for comprehensive awareness, doesn't it? Looking beyond the immediate task. Okay, for our final question today, let's get clear on the differences between some major welding processes. Question 5. What is the difference between MIG, TIG, and stick welding? Options. A, power source, filler metal, shielding gas. B, only filler metal. C, only shielding gas. D, only power source.
Yeah, to really understand and diagnose what's happening in a welding operation, an inspector needs to know what defines each process at its core.
Yeah.
The fundamental differences really come down to A, power source, filler metal, shielding gas. Those three things.
Right, so it's how those three work together that makes each one unique. Can you maybe give us a quick practical rundown? How do those differences affect what an inspector sees, or what kind of quality issues they might anticipate for each type of weld?
Absolutely. Thinking about these helps you anticipate potential problems, like having a diagnostic toolkit. Let's take power source. MIG welding, or GMAW, nearly always uses constant voltage, CV. It keeps the voltage steady, and the machine adjusts the current based on wire feed speed. For an inspector, this means you expect a fairly stable arc length. It's quite forgiving. But changes in stick out, how far the wire pokes out, can affect fusion if it varies too much. TIG, GTAW, and stick, SMAW, though, usually use constant current, CC. Current stays steady, voltage changes. This gives the welder direct control over the heat by changing the arc length, vital for TIG's precision or stick's penetration control. So if you as an inspector see a MIG setup running on CC, that's just wrong for the process, big flag. Okay, filler metal. MIG uses that continuous wire fed from a spool. It's the electrode in the filler. Makes it fast, productive, fewer stops. But an inspector needs to check the wire type matches the job material. With TIG, you've got that non-consumable tungsten electrode, and you add filler manually with a separate rod. Gives amazing control, super high-quality clean welds, but it's slower, needs more skill. An inspector checks tungsten prep. Makes sure the filler rod material is right. Stick welding is unique again. The electrode itself is coated in flux, melts, and becomes the filler. The flux does the shielding too. So an inspector needs to verify the electrode type, the classification, matches the base metal. Getting that wrong causes big problems. And lastly, shielding gas. MIG and TIG use external gas, usually from a bottle. Argon, maybe argon CO2 mixes. This gas pushes air away, protecting the molten weld pool from contamination, prevents porosity, oxidation, things like that. Stick welding. The flux coating burns and creates its own gas shield, plus a slag layer for more protection as it cools. That's why stick is so portable, no gas bottles needed. An inspector would check gas flow rates for MIG-TIG and look closely for porosity in stick welds, often sign of damp electrodes or maybe the arc length was wrong. Poor shielding. So yeah, those are the key things you're evaluating for each process to ensure it's being done right and the quality is there.
That really clarifies it. It's not just about picking a process, it's about understanding a whole different system, each with its own things for an inspector to watch out for.
Wow, okay, that was a really productive deep dive. We've gone through 5 key multi-choice questions today. But more than just answers, we've unpacked the why for GMAW spray transfer, positional MMA tricks, electrode types, the full scope of welding hazards, and what really separates MIG, TIG, and stick. This stuff is absolutely foundational for your CSWIP 3.1 exam, and honestly, even more crucial for being a really effective welding inspector out in the field.
And maybe as you carry on studying, think about this. Getting the right answer on the test sheet is one thing. But how does really understanding these core principles change how you'd react to a tricky weld defect or a safety issue you spot on site? How does knowing the why make you not just someone with a certificate, but someone who can genuinely guide decisions, ensure quality, and keep people safe? Someone truly indispensable. That's a great thought to end on. It really is about building that deep, practical insight that stays with you long after the exam. Keep digging into these concepts, keep asking those why questions, and keep sharpening that inspector's eye. We're wishing you all the best in becoming truly exceptional welding inspectors.